I'll interrupt again to introduce Ian Bradbury, who's going to talk about RGB to HDMI using a Raspberry Pi. Over to you, Ian.
Okay, right, thanks. I've been working with sort of broadcast video for most of my life, associated with computers. So I'm sort of fairly sensitive to the sort of technical quality of video. And as you can see from behind me, I've sort of been setting up a sort of vintage computer hobby room, and was looking for a really good solution to get a decent quality picture out of these old computers. Now I've tried various of the sort of standard things that are available, like the GBS 2200 and the sort of eBay converter, which you're probably familiar with. And various other ones as well, to be honest, but they all have various problems with them. Most of them tend to assume that the video that's coming into them is interlaced, TV pictures rather than non-interlaced computer video. So they try and de-interlace them, and that introduces all kinds of weird artifacts. And also the other problem they tend to have is very high lag, which is the lag is the time between the video going into the converter and the video coming out of the converter. And because of all the processing they do, they usually have multiple frames of lag. So for instance, the GBS 8200, I think, is something like 40 milliseconds, and that eBay converter is even worse than that, something of the order of 100 milliseconds. Now that doesn't sound a lot, but actually if you're doing anything like, say, using something with a mouse-driven pointer, you move the mouse, but the pointer will lag behind the movement, and it really becomes quite noticeable. Anyway, a couple of years ago, Hoglet on the Stardot forums, David Banks, announced that he'd sort of come up with this project to use a Raspberry Pi to interface to the BBC Micro. As that was sounded an interesting project, I decided to build one myself. And it worked reasonably well, but it did have some limitations. One was that it didn't de-interlace mode 7 at all, so you got sort of weaving artifacts on mode 7 pictures. You may have seen that kind of artifact on badly processed video, where you get that kind of line combing effect. It also had some lag because it didn't lock the input to the output, or the output to the input, I should say. It had about sort of 2 frames, which is about 40 milliseconds of lag. And as David made it an open source project, I decided to sort of contribute to that. And basically, I sort of built a couple of prototypes myself and started work. And the first thing I did on it was I added de-interlacing for mode 7. So now that no longer has any kind of combing artifacts. And the other thing I added was gen locking, so that the Pi Zero's output is now gen locked to the input. And once they were gen locked, there was no need for any frame delays within the system. So basically, the video is now output almost immediately after it's received on the inputs. I think the actual lag now is of the order of about 3 milliseconds. So those particular changes were the initial things I did to it. But as I said, I was setting up a vintage computer room with loads of different computers. So the next thing I wanted to look at was to see if I could get it working with other systems. The first one I tried was a PC, because again, I have some vintage PCs, and all the PC interfaces before VGA, which was the MDA, the monochrome display adapter, CGA, color display adapter, and or color graphics adapter, I should say, and EGA, which is the enhanced graphics adapter, were all TTL like the Beeb, but they had more bits per pixel. So I sort of worked with Dave, and we came up with an update to the CPLD on the system to increase the bit depth from 3 bits per pixel, which was just enough to capture the Beeb source, to 6 bits per pixel, which was enough to capture EGA, which was the highest bit depth available on the PC. Now that required then the addition of a profile system into the converter, because again the converter behaves in an unusual way. It doesn't sort of just generally accept video signals and display them. It needs to know, because it samples them precisely, it needs to know exactly, the pixel clock of the original source and the dimensions of the original source, so that it can produce the best result. The CPLD normally oversamples by about 6 times or 8 times, but only looks at every 6 or 8 pixels. So you need to align the source with the sampling points, so that it only samples on the middle of each pixel rather than at the edge, where it could sort of misread by sampling pixels, 2 pixels instead of 1. The profile system basically then allowed you to specify different machines. So I then added profiles for all the TTL computers that I could find. So you've got the Oric, these as the various PC versions, as I've mentioned. There's also QL, I think, and I think there are a few others as well that have been added recently. And then I started looking at the possibility of maybe including some of the other computers which didn't have TTL outputs, like the first one I did was the ZX81, which obviously just has a 1 bit per pixel essentially, but it's only available in an analog form. So the first thing I designed was a level converter, which basically just did took a sync level slice and a video level slice and fed those into a converter, and that worked pretty well. So I then decided to design an analog add-on interface to the original project. So the first thing I did was come up with a slight redesign. This is Dave's original design, which had a captive cable on the end, so you couldn't change it. So I then changed it so that it had a header on the end instead, so that you got the original reason for doing that was so you could plug in a ribbon cable with a PC style connector on the end. But it then became possible to put an analog interface on instead. So you basically plug that into there, and then that gave you an add-on analog interface. This was the first version. I then redesigned it a bit to make it a bit easier to change the cable. And so this is the sort of current analog interface. And again, that plugs in like that onto the board, and that plugs into the Raspberry Pi. There's a view of the Raspberry Pi connectors there. And you plug your computer into the IDC header on the end. The analog interface itself is basically a set of comparators and a DAC, rather than an A to D. So the comparators actually form a sort of primitive set of 1-bit A to D converters, and the DACs allow you to set the threshold level for the converters. The reason it's done this way is that there's only 6 bits per pixel available, and you can't sort of hang a normal A to D converter on that because you're not actually able to sort of digitize the raw analog signal. You basically have to threshold the signal so that you end up with a few bits worth of information per pixel. The analog interface allowed me to extend support to things like the Atom and the Dragon and the Tandy color computer, which are all based on the sort of 6847 video chip. And also it allowed you to pick up RGB outputs on computers which only used a limited number of RGB levels, like the Amstrad CPC 464 or the Spectrum. The later Spectrums, like the Spectrum Plus 2A and the Plus 3, had an analog RGB output, which again only had a couple of levels per RGB. The earlier Spectrum 48K has a YUV output, which does have more levels because unfortunately with the YUV, when you convert the sort of RGB to YUV, you end up with rather a large number of levels, but I was able to get a usable picture out of it, but it couldn't distinguish between the bright and the standard spectrum colors on the 48K Spectrum. And as I say, I've also added it to various monochrome computers like the UK 101, Ohio Superboard, Tandy TRS-80, Apple II, and the ZX80 and ZX81, as I've already mentioned. So it's become a very useful project for just limited to these early 8-bit computers. You wouldn't be able to use it with the later sort of 16-bit computers like the Amiga or the Atari ST because there isn't enough bit depth available on the Pi. One of the main limitations of it is the fact that the Pi's memory system is a little bit sort of unpredictable. Well, more accurately, as I suppose, it is technically predictable, but it's not. It's rather not unclear as to exactly when it's going to be, taking longer than normal to do any particular thing because it might be, writing data back from the cache to main memory at the same time that you're trying to access main memory. But for these lower bit depth and lower resolution computers, it seems to provide a very, very high quality result. The other thing I added to it was integer scaling with nearest neighbor, so that you take the original pixel that you sampled and you then replicate it over a fixed number of LCD pixels. So the end result looks extremely sharp. And it almost looks like it's coming out of an emulator rather than actually coming out of real hardware. As mentioned earlier, it isn't compatible with the NULA because it will only sample 3 or 4 levels per RGB, and of course the NULA can output up to 16 levels per RGB. So you'll end up with a picture, but it won't be an exact representation of the NULA output. However, there is another alternative on that, and that is that I added in-band palette changing, which means that you can put a stream of pixels on a video line that are actually commands to the converter to reprogram the output palette according to the values set in those commands. So the upshot is that you can say reprogram the BBC color, BBC's normal RGB output to be any colors you like. And the other feature of that is that if you display a mode 2 picture in mode 0 instead, it can actually decode all 4 bits of the original mode 2 picture rather than just the 3 bits that you normally get, and that gives you 16 colors. So in effect, you can get the same sort of output quality of the video annuler, but without actually changing the ULA. Recently, I've had some boards made in China, and I got an email yesterday to say that they've been shipped. So hopefully, I should have some of those available in the next few weeks. And the other thing I did was I redesigned the analog board. As I said, this is the original analog board, but to get this made in China was actually very expensive because some of the chips in them were relatively expensive. So I found that one of the PCB companies, JLC, has a list of components that they stock, which are, or some of them are quite cheap, and they can then build a PCB for you with those components that from stock. And so I completely redesigned the analog board using just these JLC stocked components instead. And these boards actually came back a couple of days ago. And if you just look, you can see they're very slightly different designs and a different number of chips. And this new board now costs about the same to have completely made and assembled in China and delivered here as the chips cost on this board. That meant that it was a lot more practical now to offer this board as a ready-built option compared to the original one. As I say, I've managed to add it to most of my computers in the background there. You've got to say there's a Spectrum Plus 2, a UK 101, there's a Electron there, and a Dragon and an Atom. The only one it doesn't work with at the moment is the Commodore 64, and that's because that's composite output, and the composite is generated on the chip itself. Right, so there's not normally any option to access it. But there is another open source project by Copper Dragon, which basically sniffs the bus on the Commodore 64 and regenerates or generates RGB output, which so I'm planning to fit this and hopefully get it working with the converter as well, because again, the Commodore 64 has a limited number of colors. There's only 16 possible colors it can output. I think the next thing I was going to do was to actually do a demonstration of the converter and just go through the menus to sort of so you can see what the various options do. So I'm going to have to move the camera while I do that. So if you just hold on a sec. Just to show you, there's an Amstrad CPC and a Beav there, and there's an Apple IIe and a TI 99/4A over there. Okay, so if I just clear the menu, I mean, obviously we have a standard output of a Beav there. Can you still hear me okay with that? Yeah. So you have the standard output from a Beav. Again, it's difficult to demonstrate the quality here, but there is a gallery of screen caps, because one of the other features of the converter is you can actually grab the frame buffer of the Pi and save it to the SD card. So there's a gallery of screen caps on the wiki, so you can look through those to actually sort of see the relative quality of the output. So as I say, we have the Beav output here. If I just clear the screen to show some of the menus. And these are the menus for it. You have the info menu, which gives you some information on the source, what the pixel clock is, what the clock error between the nominal pixel clock and the actual pixel clock is, the duration of lines, frame rates, pixel aspect ratios, etc. There's a system summary which shows you what the actual the Pi itself is doing. You have the PLL, the clocks that it's running, the voltages and temperatures. Calibration summary shows you the calibration values, because one thing you have to do, because it needs to sample accurately, you have to calibrate it to the individual machine. But generally, once it's calibrated, you don't need to make any further changes. And you can also update the CPLD, so you can change between an RGB or a YUV CPLD, and now there are a couple of different RGB CPLDs. The preferences menu controls the palette that you use on the output, and again, this is because it's essentially slicing levels and generating a few bits. It's essentially converting the source back into logical colors. So you need to reapply a palette to get back to the actual physical colors. So the normal palette was RGB for a beeb, but there are various other palettes available for the various supported machines. You can turn the output color from normal to monochrome, or green screen simulation, or amber screen simulation. You can invert your video, or just invert the luminance side, but that's primarily for YUV mode. You can also set a border color. This is part of the screen area that's not captured. The palette control, that's the in-band commands that I mentioned. There's various options for NTSC artifact coloring, which I'll come back to in a minute. You can simulate scan lines and vary the intensity of the scan lines. The deinterlacing of teletext, there's various different algorithms for deinterlacing. Generally, the advanced motion is the best one. The only reason the others were there was because they were implemented first. But the advanced motion one gives you sort of a pretty technically perfect deinterlacing. You can also control whether different scaling factors, and whether you're overscanning the screen area, and also the size of the screen caps. So you can vary the size of your screen captures. So as I say, I mentioned the in-band commands there. So I have a little demonstration of that here, which is these are some of the demonstration pictures from the NULA. Where it's being displayed on a beeb, but reprogramming the palette. And it does this. For instance, if I go back to the preferences menu now and turn this off, you can actually see what's being sent. And this line up here is the programming information that changes the palette. Turn this back on again. It's a great shame we didn't have that kind of palette option on the V when it first came out. Okay, we're back again. Right, so next menu is the settings menu, where you can control the font size. So you can have a small font or a larger font. The small font will automatically be selected if it can't fit the larger font on screen. VSync indicator shows, turns on this sort of red bar up here. That shows you where the relative position of the source is compared with the video from the gen locking. So if I turn off the gen locking, you can see the two are no longer locked together. If I switch it back on, it will now relock the two. The gen lock line controls the relative phase of the two pictures. When you adjust that value, it moves the relative phase of them, which is shown by the line moving. The speed controls the rate at which it will gen lock. Sometimes if you gen lock fast on a monitor, it will actually cause the monitor to lose the picture. So you can slow down the locking speed to avoid that. The gen lock adjust controls the range at which it will lock the source to the pi. Normally it's only plus or minus 5%. So if you put for example, you put a 60 hertz source into the pi and the pi is displaying a 50 hertz output, it won't gen lock. But you can adjust that so it does full range. But it's not normally recommended because it will, you can end up with some very non-standard video outputs under those circumstances. The number of buffers controls the number of buffers that are used. It's normally single buffered. The only time you use more than multiple buffers is if you're doing standards conversion. So if you were taking a 50 hertz input and displaying it on a 60 hertz monitor or something like that. The debug just turns on some debug information. The geometry menu, this controls the actual description of the source. So you've got the horizontal offset will control the capture that way, vertical offset that way. And the width, the minimum width controls the minimum amount of area to capture, which is usually the resolution of the computer that you want. So in the case of this, it's 640 by 256, which is your standard sort of BBC mode 0 resolution. You also have the maximum width, and that controls the maximum size that it will capture. The reason you need both of those is that because it does the integer scaling, the actual amount of area that is captured will vary depending upon the size of the monitor in use. So, and it adjusts it actually selects a range of a value between the minimum and the maximum to do the capturing, which will fit as an exact multiple of that on your monitor. So it will vary depending upon the monitor size. The pixel aspect ratio controls the scaling size. So, for example, if I go to 1:1 pixels rather than 2:1, you can see that the video is shrunk down. Frame buffer size, double height, can be double height, double width, and double height and width, or normal. Generally speaking, you need at least double height if you want to use scan lines. Frame buffer bits per pixel, that controls the bit depth, which can either be 8 bits per pixel or 4 bits per pixel. Clock frequency is the nominal clock frequency of the source computer. So in this case, BBC Micro, the pixel clock frequency is 16 megahertz. Line length is the number of clock cycles per video line. So again, it's 1024 for a BBC Micro. Clock tolerance is the amount of drift between the nominal frequency and the actual measured frequency that's allowed. Lines per frame is the number of lines in a video frame. This is normally sort of 312 for a sort of PAL 50 hertz system, and it would be sort of about 262, I think, for an NTSC source. And the sync type, you can switch between composite, inverted, minus, plus, horizontal verticals. Those are used for things like the PC sources, which have separate H and V sources. The vertical sync, it can again detect whether you've got interlaced or progressive sync. And the video type is progressive or teletext, which is interlaced. The sampling menu controls the various sampling options. I'm going to just put some more text on the screen to make it a bit more obvious. If you look at the text at the bottom where the menu is not on the screen, the offsets value, as you adjust that, you'll notice that it gets rather noisy, and that's because you are now sampling at the junction between 2 pixels rather than sampling in the middle of a pixel. So this needs to be adjusted. Now you can either do this manually, or there's a fully automatic option which will pick the right value. These are the values here. The divider controls the number of samples per pixel, whether it's 8 or 6. So if I do that now. Oops. Delay controls the relative position very finely, so you can shift the picture left or right. Again, this can be set automatically. This particular value is needed because it needs to know the exact position on the screen to do things like the in-band decoding or the teletext deinterlacing. VSync mux switches to a vertical sync source instead of the normal horizontal sync input. Sample mode, you've got 3 bits per pixel or 6 bits per pixel. Termination, you can either have 75 ohm termination on or off. At the moment, this is a BBC TTL output going into the analog interface, so you don't really want to terminate 5-volt TTL sources in 75 ohms, so you leave that off. These other options here only appear if you have the analog interface installed, which I do happen to have on this particular converter. So you can do it. You can use it with analog sources as well. And these set the slice levels at which it detects the various levels of RGB or sync. So what I'm going to do now is I'm just going to switch over to the Amstrad CPC. Now what I have to do now is change the profile to an Amstrad profile. So now we're looking at the output from an Amstrad CPC, which has 2 levels of RGB, or sorry, 3 levels of RGB, 3 levels each of RGB. So you have a high and a low level of green and a high and a low level of red and blue. Now, the green and red and blue are actually separately adjustable here. The green is adjustable on its own, high and low, and red and blue use the same values. Now, the reason it's split that way is that this converter also operates in YUV mode. And in YUV mode, the G is the Y version and the RB are the U and V modes. So that's why it's split that way. So if I adjust these thresholds, you can see that eventually it will sort of start going wrong. So I similarly adjust it. I don't think there's no green in this one, so that's why it's not behaving itself. Go down to this one. Yeah. So you can see you need to set these thresholds to a sensible value, but as you can see, there's usually quite a lot of adjustment range. Similarly, with the sync separator threshold, you need to set that so that you end up with a locked picture. As you can see, it's beginning to lose lock if you adjust it out of range. So basically, you need to create a profile, you have to set all these thresholds up. But once it's done, it's usually repeatable across the multiple machines. So they generally only need to be done once. The next options on the main menu are save configuration, which allows you to save an updated configuration if you've changed something. Restore default configuration will restore the factory settings. And auto calibrate video sampling will automatically adjust the offset that I showed earlier and to pick the correct sampling point. Resolution allows you to change the resolution of the source. So you've got various fixed resolutions. Unfortunately, the Pi requires a reboot when you change resolution, so you won't be able to change it without. Well, it gets changed now when you exit. I've actually put it back to itself, but it'll just reboot. The interface setting is just basically tells you what. Scaling is the next one. The scaling, again, you have various different options. You have integer sharp, which is integer scaling, where, as I say, one original pixel gets mapped onto an exact area of LCD pixels. So in this case, the resolution of the monitor is 1600 by 1200, and so one B pixel gets mapped onto, I think it's going to be 2 times 4 LCD pixels. And the sharp here means it uses nearest neighbor scaling. So those pixels are just all replicated with exactly the same color. If you select the integer soft option, it still maps to a fixed number of pixels, but uses an interpolation scaling instead of nearest neighbor. And very soft uses interpolation scaling, which is more aggressive, so it makes the picture a bit softer. Fill 4:3 basically stretches the screen, stretches the sample area to fill the screen. This is pretty much like a normal you know, a normal converter would work. Fill 4 to 3 very soft again uses the softer scaling interpolation filter. And fill all and soft and very soft are the same things again, but they will stretch to the screen size. So if you have a 16:9 screen, it would stretch it across the whole 16:9 screen. So again, I'm going to switch back to the original. Again, that's when I change it, it's going to require another reboot. So that controls the basically all the settings that are available. So the auto switch option on here allows you to select automatic switching between certain profiles. Most computers you don't need it, but on the BBC you need it because it needs to switch between a mode 7 profile and a mode 0 profile, which use different sampling parameters. And in the case of an IBM PC, you can put all the different PC profiles, the different resolutions and timings into a folder, and it will automatically pick the best one which matches the timing that you have, and that is done with the sub-profile switching option. Now, if I just change over to this other converter, this is some of the latest developments I've been working on. As I mentioned, the original analog interface could only distinguish between 3 levels on each of RG and B, or YU and V. But I did put an option on the back of the analog converter board to fit an additional comparator chip to increase that to 4 levels. And that also required an update to the CPLD on the adapter board, and I've recently got that working, and that allowed me to actually get the full 16 colors working on the Texas Instruments 994A. So again, you can see at the moment that it's producing a decent quality picture from this output. Fortunately, the TI-994 here has a YUV output. And the other option, which I mentioned earlier, was the NTSC artifacting. So if I switch over to the Apple again, what you have to do is change over to the Apple profile. You can see in this case that selecting the wrong profile often will result in almost no picture at all. Right, so now my Apple II is an NTSC one, so I'm selecting the 525 option. So you're looking at the output of an Apple II at the moment, and by default, the Apple II doesn't have a normal color output. So if I select the output there, yeah, the Apple II really has only the equivalent of sort of mode 4 and mode 0 of the BBC Micro, which are monochrome output. but if it turns its color burst on, those can produce what's so-called artifact colors on a normal NTSC monitor. So these vertical lines would be treated by an NTSC monitor as color information, and it would produce a color picture on an NTSC monitor. So I've added some software in the latest version to allow you to switch on NTSC artifact colors, and it now decodes those. And that's what these options I had mentioned previously in here were for. So you have, you can vary the sort of tint of the colors, saturation, contrast, brightness. So on. So I think that's it at the moment.
Thanks, Ian. That's really good. Just one thing I wanted to say on behalf of people who might be interested in using this gear. With all the profiles already set up, it more or less works straight out of the box, I think. So,
yes, right.
yeah, so it's great that we've got all these on-screen displays, and almost everything can be tweaked and new profiles can be created. But actually what you get out of the box is a sort of pixel perfect, rock steady HDMI output, which with massively low latency, which I don't think can be beat anywhere, which is brilliant. And the other, I'm not sure if you mentioned it, but it's rather handy. It's got the ability to capture the screen onto the SD card.
Yes, I did mention that.
Oh, you did? Great. I mean, that's really good as well. When you need it, you really need it.
So, Ian, is it working with a PAL Apple II at the moment? Because obviously that's got additional circuitry which sort of gets around or deals with the NTSC artifacts on board.
Yeah, then basically that circuitry sort of essentially has an NTSC decoder, which then re-encodes in PAL. So it does make a rather noisy mess of the thing. I believe there's a switch. As I say, unfortunately, mine's an NTSC Apple II, so I don't know for certain, but I believe that there is a switch on the motherboard of the PAL Apple IIe to actually switch off the PAL coding and put it back into sort of basically an NTSC machine.
I'll have a look. I've got a PAL one here, so if you want me to have a look and poke, I'm more than happy to look and poke.
Yeah. So, so yes, as I say, I'm quite pleased with this redesign of the analog board now with that one, because so I designed that, sent the files off to JLC, and got these completely finished boards back a couple of days ago, and they worked first time. I was really pleased. There was only one slight mistake. I got the there's a protection diode for when you are powering from the computer, and I managed to get that the wrong way around. But that was the only. But fortunately, that's about the easiest thing to fix on a board like this. I mean, to actually build this would be a bit of a nightmare, because it's all using the much smaller components than this version. So yeah, I mean, in fact, actually, this particular version is not really practical to build, because the DAC that's on it is just not available, and you can get it from China, but you can't get it from sort of RS or Farnell or DigiKey or Mauser or those companies. So this version will still be the DIY option, but this version will be the sort of ready-built option.
Yeah, just a comment from my side. A great presentation, by the way. But having spent a couple of years dealing with people that really know about video, teaching me everything about video, trust me, I thought it was as simple as turning on a TV. But I learned quite a long and painful lesson that there are guys out there that really, really concentrate on what things look like. It was really impressive, the amount of configuration you have in there. It was amazing work. I mean, I should get my hands on one and have a play with it. I'd really like to see that, because I know that like shifting a pixel from like a micrometer to one side makes some people very happy. We had a lot of this with the LD decode stuff. I have never looked in so much detail. It's like, oh yeah, you're right. There is a very slightly fuzzy line there if you use a Electron scanning microscope to look at the screen. So it's really cool what you've done.
What is the story on availability there, Ian? Because I guess a dozen or more of these must be out in the field, maybe much more.
Oh, I think there's probably 100 of them at least built now, something of that order. You know, based on the sort of communication I've had with people, and you know, the number of boards I've sent out blank boards, quite a lot of blank boards now, and I know a lot of other people have ordered blank boards and also distributed them around. So, but as I say, this I've just done the first batch order. But the problem is that when you get stuff made in China, there's like several different companies you can go to, and PCBWay is one, for example, that will make boards for you, and they will also build stuff up. But they can build stuff. They'll build anything basically, as long as you can provide them with a list of manufacturers' part numbers. They will make it. And I've had to order the main board, this part, from PCBWay because JLC don't stock the CPLD that's used on this board. So unfortunately they're more expensive than JLC for this, so it does make this a little bit more complicated. But as I say, I've just had an email yesterday from them to say that these have been built and they've been dispatched, so I should have a few available within a couple of weeks, I suppose, depending upon how long the delivery is.
Oh, that's great.
But as I say, with the analog board, the new analog design, that was made by JLC, and they are really quite low cost, very, very competitive pricing, because basically they're only building it from the components they stock.
I have to say, and building them manually, I think I said in the thread, they were quite a pleasure to build, and I've built quite a few different SM surface mount things from different people. So they're the layout lends itself, certainly in the bits that I've done, to have assembly very, very nicely.
Yeah. As I say, it's well, obviously the layout of this is mostly Dave's layout.
Yeah.
I just modified it. But the analog board was my layout. Yeah.
Can I just echo what Simon said? For another brilliant presentation. And I think I unfortunately missed the first 10 minutes of it, but from the bit that I saw, there's quite a bit of overlap with the Doomsday project. Well, to my mind, especially apart from the Doomsday project, the IBM PC gen locking thing. Am I right in understanding that there's you can do like proper gen locking? There's like a second analog source. What I'd like to be able to do, I don't know if this is possible. We used to have a gen locking board that took the output from a video disc player, mixed it with an EGA signal, and you could select like translucency levels for all the 16 EGA colors, and have a transparency for just one color. I saw that there were a few IBM PC profiles, but what I was wondering was, is there also a serial port style interface where you can send it codes to turn on and off transparency and stuff? Because that'd let me emulate so many interactive video projects from the 80s. Yeah, that's it basically. I'll have to email you or,
Right.
Or get in touch sometime to give you a full list of questions about that.
I don't think you'd be able to do what you want in that respect, because you'd need two sources going into the Pi for it to sort of mix between. you know, I mean, you could say, I mean, there isn't at the moment, but there is a serial port on the thing, which is mainly used for debugging. But you know, you could add the serial port commands to do things, you know, to manipulate palettes and what have you. But what you're talking about there is essentially keying. You know, there's two things. There's gen locking, which gen locks the signals together, and then there's keying, which is overlaying one signal over another. You know, with an alpha channel to control transparency, and that's two different things.
Yeah, that's it. I've had this conversation with Simon about the terminology of what I used to call gen locking is what you call keying. But yeah, I mean, how much work would it be to add a second analog input from the Pi? Basically, all you do with the IBX with the video logic stuff is 16 colors, EGA colors, and mixed in with I say only, it's probably a huge amount of work actually, but how much work would that be to have a second analog input?
I'm not sure it's really practical at the moment. The main thing that we're running into at the moment is that the bandwidth of the Pi to actually handle more information, more bit depth is restricted. Because, as I say, because of the unpredictability of the memory timing, you know, although like, you know, 95% of the time it would be able to, you know, handle a greater bit depth, 5% of the time it wouldn't. And therefore, you know, you would obviously get an unusable picture because it's basically doing this in real time in software. It's, you know, continually sampling. What it really needs is a FIFO buffer on the incoming video data, which will sort of basically allow you to continually capture at the incoming rate. And therefore, if you've got a little bit of uneven processing time, the FIFO will smooth that out.
Yeah, I'm not really a hardware person, but to my sort of simplistic way of thinking, could there not be some sort of analog electronic and digital hybrid, that because they mixed the signals back in the 80s, it wasn't a digital board at all. It was all done with sort of analog mixing. Maybe interface a bit of analog circuitry with the Pi for the. Yeah,
I think I could add a little bit to this, Phil, because I mean it's a little bit tricky because the gen locking that used to be done wasn't based on digital frame buffering. It's a little bit different what's going on in the hardware there. One of the things that I looked at, and I think there is commonality, but it's commonality in the fact that the code that Ian and the rest of the guys are producing is open source that can be reused. Because I was looking at solutions like using the D10 FPGA, because for a start, it has an FPGA on it, which is more powerful than the CPLD and can do more things. But the other thing is it has a hard ARM processor on the other side. So you can actually run Linux on the FPGA. And then you can do things like, if you want to emulate a Laserdisc player, for example, or a secondary video source, you can emulate that on the Linux side and then use the FPGA as a frame buffer to produce those graphics, and then mix it with the inbound graphics in the same way that the solution that Ian's talking about is currently doing it. So you kind of have a secondary source built into it, but it's much more powerful hardware. I mean, you're talking a couple $100 just for the board that you would do it on. So I mean, there's definitely possibilities to mix those techniques together, but it's a different hardware problem, I think.
Right. I was that leads me to my last question, which was how much you've actually added to it there, but how much? So £200, did you say, or $200 for that board? And how much is Ian B's board, the sort of the full setup? How much does the manufacture in China and the Pi and that all add up to as a cost?
I haven't finalised the cost yet, because, as I said, I'm probably going to have to end up paying import duty and VAT and what have you on the boards when they come in. So I don't know, but it's you know, relatively low cost. It's only like you know, tens of pounds. It's not hundreds of pounds.
And just one last quick comment as well. When you were showing the Nuler stuff, you said it's a shame we didn't have colour palette stuff back in back in the day. We actually, the company I worked for, we produced a colour palette board for the BBC in 1983, 1 year after it came out. So
yeah, I know. I designed one of those as well for another company.
I was counting down the seconds until Phil said that.
I knew you would be, Simon.
But one other thing I've got to mention, I found a nice little case on eBay, which is a sort of standard Raspberry Pi Zero case, which it all fits into. Fortunately, it's just the right height to sort of take the extension board. But the problem was getting the holes in the right place. I actually designed a template PCB, which is basically the standard PCB design with all the tracks ripped off and large holes in it. And you just drop that inside the lid, and it's got little tabs on it. You can just sort of see there, so that it holds it in the right place. And then you just drill through that, and then you get all the holes in the right place for the case.
Yeah, just to echo what Simon said again, I mean, it's amazing, all those different settings. It's going to be useful for many genres of retro computers, I'm sure. Sure it'll be very popular.
As I say, the only real issue is that it doesn't do composite. So and a lot of American stuff, sort of all the Atari stuff and all the Commodore stuff, is all composite out of the chip, and therefore it's very difficult to sort of get a clean signal to put into a converter like this. As I say, there are obviously these other open source projects which I mentioned, like this one, that will potentially allow you to get a digital signal out of them. And so I'm hoping that one will allow me to get the thing working on the Commodore 64.
Doing overlay, I would suggest you either you use a more powerful Pi, so you've got more cores, and then you can do. So the Pi Zero is brilliant but it has only got one core. The other slight option is to use the VPU1 to do the sampling, and then that could give you the buffer.
Yeah, and that's what I've been looking at as the next possible thing, because obviously you and Dave have been doing that with the second processor, PiTube Direct, and your 1 megahertz bus solution as well.
Yes. The other thing is, it would be possible to. I don't think anybody's done it, but it's theoretically possible to have some cores that do bare metal and some cores on the bigger Pis that run the Linux. So for people who want to do that sort of thing, that would be theoretically possible, but I don't think that's in our zone.
Yeah. The other interesting thing is that the Pi 2 and 3 are actually slower than the Pi Zero for this particular project, because it seems the uncached memory access time, because obviously this project basically spends all its time once everything's set up, it's spending all its time in a loop, capturing data and writing it to the Pi's memory. And of course, it's writing it to the screen memory, which is marked as uncached memory. So on the Pi 3, the uncached memory access is actually about 20% slower than on the Pi Zero. On the Pi 4, it's all a lot faster.
Yeah. The other way to do that is to actually mark it as cached and flush a line out. So every time you get to an H-sync pulse, just flush the line out.
Yeah.
Cache, because then what it will end up doing is doing massive burst writes to the RAM. Rather than marking it as cached, as uncached. Whereas when it's uncached, it's doing single writes out.
Yeah.
So Dominic, is there any like dual or quad bare metal that you said that you can set one as bare metal and another as for running the proper Linux? Is there anything where you can have sort of dual bare metal modes, if that makes any kind of sense?
That's really easy. All you have to do is just you set a memory pointer to where you want the kernel for the next core to be, and then you say go to that core, and you can do it for all 4 cores. So multi-core bare metal is really easy.
The reason I was asking, that was really interesting what you said about using a second core for doing the second analog input, but I'm still not 100% sure what I'm missing on the analog side. Why would we need to use all that processing power to capture into a frame the thing? Could we not do
You could do it all back
1980s style?
You could do it 1980s style, but I'm afraid I think you'll be on your own, because I think everybody else will just want to do it in the digital domain.
Yeah.
The actual Pi only sees digital. There is no analog actually in the Pi.
No, but if you had a little sort of analog board add-on that the Pi could poke with a couple of GPIO, but I know it'd be much less flexible, but there weren't that many. The digital side, the sort of text modes, EGA, CGA modes, there weren't that many modes on that side of it that back on the IBM PC, and I don't know, you'd only need to cater really for sort of this kind of output, PAL output from a laser. So while it'd be less flexible, it would only have to be keying or mixing or whatever you want to call it, sort of a standard PAL output from a Laserdisc player. I don't know, so it's just my limitations on my sort of hardware knowledge there, but I don't know if it makes any sense at all.
It's certainly a strategy.
Yeah.
Ian, thanks for the talk. It was really great. I've got one of Hoglett's original first batch machine, RGB to HDMI, and a newer one. I don't think they're on the latest software, but I've got a few suggestions if that's okay. I know it's open source, so I could do it myself, but see what you think. I think there's an option that dims the menu text when you're trying to adjust the settings for the Pi, but I couldn't find one for dimming the BBC text, so I could actually read the menu text.
Well, it dims BBC text normally.
Okay, just my setup then. Okay, second idea then. How about a test card program for each machine so it could fully auto calibrate, so you wouldn't need to change the sync levels manually
yeah, I mean that's certainly something to look at in the future. I mean, to be honest, you don't really need to tweak them. The only ones I've noticed that you need to tweak really are a couple of the YUV ones, the Spectrum one and the Spectrum 48K one, and the TI-99 4A, because their thresholds are very, very close together, you know, and so they're likely to vary quite a lot from machine to machine. But certainly for things like the RGB on the Amstrad CPC or the RGB on the later Spectrums, and probably even the Atom as well, the levels seem to be quite large, and they don't really need to be tweaked much, if at all.
Okay.
So, but it's you know, but it's probably a good thing to have a, you know, at least, you know, I mean, you know, a test card would really make sure that every machine was optimized for, you know, for each one. So yeah, it's something to look at certainly.
And the other one's probably not practical, too much work, was a way to control it from the Beagle, whatever the machine is, the whole menu system. I guess you don't really need to go in it once it's set up, so that's probably not.
Yeah, I mean, it's, you know, the menu is great to go and play around with and, you know, experiment with new profiles, but once it's really set up, you just forget about it and turn the thing on, and it just works once you've got everything set up.
And does it still detect mode 7 via the H-Sync pulse?
Yes, it does.
Yeah. What? No, yeah.
I was going to say on that note, very quickly, it mentioned deinterlacing for mode 7. What happens if you use sort of mode 1 or mode 0 in interlaced?
It's treated as progressive, even if you've got interlace sync turned on, which is so you always end up with the same picture quality.
Okay.
I had one additional thing just when you were talking about the case and the template that you made. When I made the cases for the Beep SCSI, like this little one you can see, the way that I did it was to take the circuit board design out of KiCad, and there's actually a way of exporting the circuit board and pulling it into the CAD like OpenSCAD, and then you can actually like have a picture of the circuit board and just design the case around it for 3D printing. Yeah. It's a really fast and easy way to make even quite complicated cases.
But as I say, in this case, it was easy to just buy this off eBay.
The nice thing about 3D cases is that you can just pull them from GitHub, press a button, and produce a case. So it's a really fast way. But getting the chain where you can pull the boards out of your circuit, your what do they call them, EDS or whatever, into OpenSCAD and stuff, it means it takes about 10-20 minutes to do a case that way. Pretty fast way.
I missed the earlier bit of your talk. Did you talk about the in-band reprogramming of the palette?
Yes. Yeah.
Is it possible to do that with ruptures on the screen, so you can reprogram it partway down the screen?
No. Yes and no. No, in that it won't work in the way that you're thinking of, but I did, again, the in-band stuff is all still a bit sort of experimental. I just implemented it some time back, but went off to adapt it for more computers. But I really need to revisit that and, define a proper protocol and, get everything finalized on that, and then write a driver. But the one thing I did do an experimental test with is you can reprogram the palette using up to 16 different palette entries. So 16 lots of 16 colors, and then you can specify bands of the screen in each of the palettes. So it's not an interrupt driven change. It's actually, you can pre-program, lines 10 to 20 are this 16 color set. Lines 21 to 50 are this color set. Lines 51 to 70 are that color set. And that actually works. I tested that.
And you could do that each frame in theory.
Yes, in theory. Well, you could change it every frame, I suppose. Or you could just program it once and it will just do it statically.
Yeah. So I mean, I guess if you're doing it statically, it's like having a screen overlay. Like on a Vectrex. But if you were dynamically fiddling with these things, you could also deal with that situation by just reprogramming it every frame.
Yeah.
That's a nice idea. I like that.
If you come back to look at it again, would it be possible to split the screen in the middle and have one palette on the left and one on the right? Comes up occasionally.
Yeah, I suppose so. I mean, that's a little more tricky because you have to sort of you'd have to keep track of an incoming sample count in order to switch over to the alternate etc. Basically, the way that it works is it uses an 8-bit frame buffer. And it writes obviously the lower 4 bits are the 16 colors of your beeb, and then the upper 4 bits are what palette that should be displaying in. So basically, at the moment, it's just on every new line, it says, right, all the pixels on this line have the top byte, the top nibble being set to this value. So you'd have to change the top nibble halfway down the line. So it's technically possible, yeah. Whether there's enough CPU cycles left to sort of add that kind of code, I'm not sure.
Presumably, if you're just overwriting it, I guess if you're just overwriting it, you can just fill them in to start with and leave them.
Yeah.
But yeah, I guess like you say, there's also where exactly is the middle.
It's, as I said, the biggest problem in at the moment is the tight timing on everything. Although there are plenty of CPU cycles left because of the sort of rather unpredictable nature of the memory system, you've got to sort of you're limited to a lot fewer cycles than are available in the theoretical maximum. You know, you basically once you exceed a minimum number, things start to break down. Even though the total number, you know, there might be like, you know, 75% more CPU time available, but it's not distributed evenly. So, like I said, this is where hopefully using the VPU to implement a sort of software FIFO buffer will get around that, and that would allow a lot more potential experimentation to be possible there.